take a look at this sample problem. Okay, so actually for the chapter 21, the theory and also the problem will be really simple. So just like the high school physics, I think you should have learned it before. But anyway, just for the completeness, I will just go through it. Okay, so for this one, sample problem 2101, okay, it says figure A shows two positively charged particles fixed in place on an x-axis. Okay, so this is x-axis, and the charge are Q1 and Q2. Okay, this one is Q1, this one is Q2, and the particle separation is capital R. Okay, this is the separation. What are the magnitude and direction of the electrostatic force on particle 1 from particle 2? Okay, so actually asking about this force acting on Q1 due to particle 2. Okay, so this is really easy. So we just need to apply the Coulomb's law. So F12 will be just K times Q1, Q2 over R squared. Or actually you can just try to take the absolute value. So we try to calculate the magnitude of the force first, okay, without considering the direction. We may just consider the direction individually. Okay, so here we just need to plug in all the numbers. For the K is 8.99 times 10 to the 9th power, and then Q1 is actually this one, so 1.6 times 10 to minus 19, and then Q2 is this one, 3.2 times 10 to minus 19, and then R, actually this R is capital R, so we may write it as capital R here, so it is actually 0.02 quantity square. Okay, so you just need to press the calculator, and then you can see this is actually 1.15 times 10 to minus 24th power Newton. Okay, so actually this is the magnitude. Okay, so actually we can also design the direction of this force. Both of the charge are positive, so which means that they repel each other, which means F12 points to the left side, or in other words, it is actually the negative x-axis. Okay, for the right side is a positive x-axis. So we may use the unit vector system to the unit vector system in Cartesian coordinate to represent F12 will be 1.15 times 10 to minus 24, and then the unit vector for the x-axis will be I hat, okay, with a negative sign, okay, which means that it is pointing to the left side. Okay, so actually for the unit vector, I just slightly talk about it. The unit vector in Cartesian coordinate, OK， 就是这个是直角坐标系，或者是叫笛卡尔坐标系嘛。那单位向量嘛。那 x 轴的 x-axis for the x-axis, we use I hat. Sometimes I just write a dot here, but in the textbook it will be written as I hat without the dot, and then for the y-axis J, and then for z-axis K. Okay, so actually IJK, and actually the unit for the unit vector, the magnitude of the unit vector will be always 1, okay, which is the 单位这个是直角坐标系的单位向量的长度都是 e. Okay, so actually this one Okay, so and later on we will make use of the unit vector in the Cartesian coordinate to calculate something like the inner product, cross product, something like that. Okay, so for B, okay, it says in figure C is identically to the previous one except for particle 3 now lies on the x-axis between particle 1 and particle 2. Okay, which means Q1 and Q2 are the same as the previous case, but here we insert Q3 here. Okay, so for P particle 3, it has Q3 to be negative 3.2 times 10 to minus 19 Coulomb, and is at a distance 3r over 4, okay, from particle 1. What is the net electrostatic force on particle 1 due to particle 2 and 3? Okay, so here we have 3 particles, so actually there will be 2 forces acting on Q1. So one of it is from Q2, which we have already calculated here. So we already have F12 to be negative 1.15 times 10 to minus 24 Newton I hat. And we also need to calculate F13, and then we finally add them together as a vector sum. But fortunately, they are on the same axis, so acting these 2 vectors together will be easy. Okay, so here we actually need to calculate F13 to be K times absolute value of Q1 times the absolute value of Q3 over the distance is actually 3r over 4 quantity squared. Okay, so we just need to plug in all the numbers, 8.99 times 10 to the 9th power, and then times Q1 is still 1.6 times 10 to minus 19, and then times Q3, the absolute value will be 3.2 times 10 to minus 19, all over 3 times 0.02 all over 4, and then quantity squared. Okay, so this is actually 2.05 times 10 to negative 24 Newton. Okay, so and as much as Q1 is positive, Q3 is negative, so these 2 charges attract each other, which means that F13 points to the y side, so which means we have F13 equals 2.05 times 10 to minus 24 n I hat. So F1 net will be F12 plus F13, which will be negative 1.15 times 10 to minus 24 plus 2.05 times 10 to minus 24, and then all multiplied by I hat. Okay, so this number will be 9 times 10 to minus 24 Newton I hat. Okay, so still very easy. Okay, so for part C, okay, it says for figure E is identical to the previous one except the particle 4 is now included. Okay, so we don't have Q3 anymore. Here we have Q4, but Q4 is not on the x-axis. So it says it has a charge Q4 with the same charge amount as Q3. It's at distance 3r over 4, still 3r over 4 from particle 1, but it lies on a line that makes an angle. Theta equals 60 degrees with the x-axis. Okay, so this is theta equals 60 degrees. Okay, what is the electrostatic force on particle 1 due to particle 2 and 4? Okay, so here we still have F12 to the same value, and here we would like to calculate F14. F14 is actually having the same value as F13 because the distance are the same, also the charge amount are the same. So the only difference is the direction. Okay, so actually we still have F14 to be 2.05 times 10 to minus 24 Newton. Okay, so but here we actually need to calculate is x-axis component and y-axis component so that we can add these two vectors together, which means F12 and F14 together. Because this is positive, this is negative, so F14 should point to the top right direction. So in such a way, we need to decompose it in the x-axis and also the y-axis component. Okay, so actually we have a F14 to be 2.05 times 10 to minus 24. Okay, so this is theta equals 60 degree. So, and which means that we need to multiply by cosine of 60 degree. Cosine of 60 degree here. Okay, so n and then I hat. Okay, positive x-axis. And then plus 2.05 times 10 to minus 24. And then times sine of 60 degree. And then here is a positive y-axis. So we have a j hat. Okay. Okay, so F1 net in this case will be F12 plus F14. Okay, so so you just need to add the x-axis component together and then together with the y-axis component. So so actually the answer will be minus 1.25 times 10 to minus 25 and I hat and then plus 1.78 times 10 to negative 24 and j hat. Okay, so a long long answer in the unit vector notation. Okay, unit vector notation. Okay, in some of the selected problem you will see this term. Okay, if it asks you to represent your answer in the unit vector notation, which means that you write your answer in terms of something like I hat, j hat multiplied by something, add them together, something like that. Okay, so any questions? I think no questions. Very easy. Okay, so here we have another sample problem. Okay, so it says figure A shows two particles fixed in place, a particle of charge Q1. Okay, so we have Q1 at the origin. Okay, this is Q1 and a particle charge Q2 at x equals L. Okay, x equals L. Okay, at what point other than infinitely far away can a proton can be placed so that it is in equilibrium? Equilibrium. It means that the net force on it is zero. Okay, so there's just no force acting on it. So in that way, there will be no force acting on it, so there will be no acceleration. So that assuming it is at rest at the beginning, so it won't move later on. But we actually need to fix Q1 and Q2 days. Otherwise, Q1 and Q2 will move later on. But anyway, so it is said, okay, so for this problem, it says equilibrium means the net force acting on this proton is zero. Okay, if you will learn the control theory later on, than when we talk about equilibrium or stability, something like that. Okay, so here it asks you also about, is that equilibrium point stable or unstable? So actually in this problem, this stable and or unstable is not that rigorous， 就不是那么严谨的。就是如果你们未来如果学那个 control theory 的话，那讨论 stability 的话是比较复杂一些的，需要用上一些像什么 Laplace transform 之类的东西去判断的。那这个就比较简单一些的，不过就 OK 就看看吧。Okay, so actually here we have Q1 and Q2. We already assumed these two particles to be fixed there, and then we try to place P on the x-axis. At least we can simply determine that it should be on the x-axis. Otherwise, if P is somewhere there, so there must be some y-axis component which can be perfectly cancelled. So in that case, it is not possible that P is not on x-axis. So at very least we can assume that P must be on the x-axis. So here we have three regions. We can simply determine that whether any of the regions are possible for the P to be there. Okay, so for the first case, if P to be placed between Q1 and Q2, okay, so the proton, okay, so you see it is a proton, 质子嘛，质子 is a positive charge, okay, and Q1 is a positive charge, Q2 is a negative charge. So in such a way, Q1 and P repel each other, which means that F1 points to the right side, and this is positive, this is negative, so P and Q2 attract each other, okay, which means that F2 also point to the right side. So F1 and F2 it's not possible to cancel each other perfectly. So we will simply reject this case, okay. And then for the next case, if we assume that this proton is placed on the left side, so in such a way Q1 and the proton repel each other, which means that F1 points to the left side, and then this proton is positive, this is negative, so they attract each other. So F2 points to the right side. And whether F1 and F2 can perfectly cancel each other, then the answer is no. The answer is no, because you can, even though you don't really calculate the number, but at least you can simply determine that Q1 is positive AQ, and then Q2 is negative 2Q. Okay, in terms of magnitude, Q1 is larger. Okay. So and for the Coulomb's force, actually it is like F equals K times Q1 Q2 over R squared. Okay, which means that if the charge is larger, the force should be stronger if R is fixed. Okay, so here we can see that Q1 is larger than Q2. Okay, so maybe this Q1 Q2 is maybe I just change I use capital Q1 and capital Q2 there, so that these two notations do not conflict with each other. Okay, so here we already observed that Q1 is greater than Q2, and here we can also observe that the distance from the proton to Q1, let's say this R1 must be smaller than R2. Okay, R1 is smaller than R2. Okay, and also we can see that the distance is at the denominator. Okay, so which means that if we have a smaller distance, the force should also be larger. So in that case, F1 must be larger than F2. Okay, so in that case, it should have no way to cancel each other. Okay, so and the remaining condition is like this one. Okay, I do not try to go through it thoroughly. You can try to think about it by yourself if you have interest. But anyway, if the proton is placed on the right side, yeah, it is possible that F1 and F2 can be cancelled and can be perfectly cancel each other for a specific point only. Okay, so here we try to calculate what is that point, okay, as the equilibrium point. Okay, so here, yeah, so we have a absolute value of F1 equals absolute value of F2. Okay, so for the F1 we have K times absolute value of Q1 times the absolute value of QP. Okay, QP is the charge of a proton. Okay, yeah, and yeah, and the distance. Okay, for the distance, suppose this is x. Okay, this is x, and this is L. This is L. Okay, so from Q1 to the proton should be x. So we have x squared here. And for the F2, we also have K, and then absolute value of Q2, and then times absolute value of QP. Okay, and then for the distance here, from the Q2 to the proton, this one should be x minus L. So we have a x minus L all square. Okay, so actually we don't need to care about what QP is because it can cancel each other. Okay, also we can cancel K, and actually we have a Q1 is actually 8Q. Okay, and this one is actually 2Q. Okay, after taking the absolute value from here and here. Okay, so here we have 8Q and 2Q. So also Q and Q can also cancel each other. So we don't need to care about what Q is. So in such a way, we can try to simplify this equation. So we just moving this term to the left side, moving this term to the right side. Okay, so we have 8 times this term, and yeah, and actually we can still cancel these 2 with this 8 down to a 4. Okay, so here we have a 4x squared minus 8xl plus 4l squared equals x squared. Okay, so finally we have a 3x squared minus 8xl plus 4l squared to be 0. So this is just a quadratic equation with single unknown. Okay, you assume that L is a fixed value, so we can actually solve x. Okay, so actually we have two solution. One is x equals 2 over 3L, and the other solution is 2L. Okay, so for quadratic equation, we should have 2 equations, except the case that we have a repeated roots, but not for this case. So actually, we have 2 solutions. Whether both of them okay. So actually, if x is 2 over 3L, which means that the particle will be somewhere like here. Okay, this is x equals 2 over 3L. Okay, which is not okay because according to the discussion here, we already know that it is only possible that the proton must be on the right side, which means that we should have x to be larger than L. X should be larger than L. Okay, so this one is smaller than L, so we will reject or discard this solution. Okay, so the only solution will be x equals 2L. X equals 2L. Okay, so actually this is actually the solution for the for the first question, and it also asks you whether it is stable or not. Okay, so actually, simply speaking, the answer is this is unstable. This is unstable. This is unstable. Why? Why? Okay, let me add a page so that we have some space. So actually, let me try to draw this thing again. Okay, so here we have this this proton, and then we have F1 and also F2. Okay, so if it is perfectly placed on x equals 2L, then the the net force will be perfectly zero. Okay, so here we would like to discuss whether it's stable. Like if we try to slightly move this proton to the right side or to the left side, okay, whether we will go back. If it can go back, we'll consider it is stable. If it can't go back, we'll consider it is unstable. It's just like that. It's just like if I try to, let's say this pen is not able to stand up. But yeah, for the kids, we somehow like to doing something like try to make it standing up. Okay, and actually, if it is standing up for a few seconds, actually this is we will consider it's an equilibrium point, but actually it's not stable because if there are some wind or if you just breathe strongly, then it will fall down. Then we'll consider it's not stable. Although it's not so rigorous for the control theory sense, but actually here we just discuss it like this. So here we try to consider if this x is having a variation like delta L. If delta L is very small, we'll consider F net acting on this proton will be K times 8Q. 8Q is Q1, and then we have also QP, okay, over 2L. Okay, here we already know that x is 2L and then plus delta L, okay, square, and then minus K times negative 2Q, 2Q, okay, we already take the absolute value, and then QP, and then over, okay, so actually, Q1 is there, and then Q2 is here. So this is 0, L, and 2L. Okay, so this distance will be L plus delta L only. Okay, and then quantity square. Like this. Okay, so in such a way we can try to do some calculation. Actually, we can see that we have K, we have Q, we have QP, we also have a factor of 2, so that we can just factor all this thing out. So we have a 2K Q QP, okay, and then we have 4 over 4L plus delta L, 2L plus delta L, and then quantity square, minus 1 over L plus delta L quantity square. Okay, like this. And then we can try to expand it. Okay, so we still have a 2K Q QP. Okay, these numbers are not important anymore, it's just a positive number. So here we have 4 over 4L square plus 4L delta L plus delta L square, and then minus L square plus 2L delta L plus delta L square, like this. Okay, so here we try to do something more, okay, which is like we try to divide by 4 and then divide by 4 for the first term. So we have 1 over, this is L squared plus L times delta L plus delta L squared over 4, and then minus, this is still the same thing, 2L plus delta L plus delta L squared. Okay, so here we assume that delta L is much smaller than L. This variation is very small comparative to the original L. Okay, so which means that for this square term, we just assume it to be very, very small. Okay, so we just ignore this term. So by comparing this one and this one, L squared are the same, and then this term is L times delta L, this is 2L times delta L. Okay, so which means that for the denominator, this is larger, which means that for the whole term, this is smaller. Okay, so which means that this is, if delta L is positive, this is actually a positive value, which means that if we slightly push this proton to the right side for a delta L, okay, the force will be positive, which means point to the right side, F net, okay, which makes it even go further away to the right side. So it means that it makes this equilibrium point unstable. Yeah, you can also argue that if delta L is negative, which means that if we just push it slightly to the left side, and then and then the F net will also point to the left side. So in such a way, this is not a stable equilibrium point. Okay, comparing with mechanics analogy. Okay, you can consider if we have a surface like this, if we place a ball here, okay, in such a way, this is stable. This is stable. If we try to push this ball to the right side, it will go back if your force is removed. And in another way, if the surface is somehow like this, actually you can also place a ball on the top. Yeah. But if there are some force acting on it slightly to the right side, then this ball will fall away, okay, or to the left side, okay. So in such a way, we will consider this is an unstable equilibrium point. Okay, so far any questions? Okay, no questions. No. No. Okay, so just move forward. Okay, so here we will talk about charges quantized, 就是电荷量子化. Okay, so actually this is easy. So it says, so electric charge is quantized, which means that we can only return any charge to be an integral multiple of the elementary charge. Okay, which means that so if we write in formula, it will be like Q equals N times E. Okay, N times E. Okay, for any charge, okay, will be a multiple of the elementary charge with an integer. Okay, it can be a positive or negative integer, or even zero if there is no charge. Okay, so which means that this n is an integer. This n is an integer. Okay, and then this e, we call it the elementary charge, 就是基本电荷. Okay, 基本电荷. Okay, so and actually this value is 1.602 times 10 to minus 19 Coulomb. Okay, so usually we will just use it up to the second significant digit, like 1.6 times 10 to minus 19 Coulomb is usually enough. It's usually enough. Okay, so here it says the charges for the free particles in an atom. So we already know that we have proton, neutron, and electron. So for the electron, we have a negative E. For the proton, we have positive E, and then for neutron, we have zero charge. Okay, just as what you have learned in high school chemistry. Okay, so here it says when a physical quantity such as a charge can have only discrete values, okay, 就是一些离散的值离散的值 discrete values rather than any values, we say that the quantity is quantized 就是量子化. Okay, it is possible, for example, to find a particle that is no charge at all of charge 10e minus 6e, but not a particle with a charge of 3.57 e. Okay, not possible to be a fractional number. Okay, so here we have a quick checkpoint we have to talk about. So it says initially sphere A has a charge of negative 50e. Okay, sphere A, we have a charge of negative 50e. Okay, and sphere B has a charge of positive 20e. Okay, the spheres are made of conducting material and are identical in size. If the spheres then touch, what is the resulting charge on sphere A? Okay. Okay, so here we have the keywords as are made of conducting material that are identical in size. Okay, so after they touch each other, their charge will be equally shared. Okay, so it asks you after they touch each other, what is the resulting charge on sphere A? What's that? OK， 没人回答吗？不好，负15啊，负15 ，OK， 很简单 ，OK。So actually it's just like negative 50 e and then plus 20 e. Okay, so actually so far, actually in the next slides we'll talk about the charge cannot be charge is conservative 就是电荷守恒 Okay, so which means that before they touch we have altogether negative 30 e. Okay, so after they touch they should also have the total amount of charge. Okay, so we should add them together and then divide by 2, and then which means that half of it is distributed to sphere A, and the remaining charge is at sphere B. Okay, so in this case negative 50 plus 20e will be negative 30 divided by 2 will be negative 15e. Okay. Okay, so so here we also have a sample problem. Okay, so it says the nucleus in an iron atom has a radius of about 4 times 10 to minus 15 meter and contains 26 protons. What is the magnitude of the repulsive electrostatic force between the two of the protons that are separated by this distance? Okay, so this is easy. It doesn't worth you to think about how to do that. It is a really simple problem. Actually the problem itself is not ask you to calculate the value. yeah, it want to test another story. So let's go through it quickly. So the force is actually like F equals K times E square over R square. Okay, it asks you what are the repulsive force between two of the protons that are separate. So both of the protons have a charge of E. So we have E square here, and then we have R square. So we can just plug in the number 8.99 times 10 to the 9th power, and then we have for the proton is 1.6 times 10 to minus 19 quantity square, and then we have 4 times 10 to minus 15 square. Okay, so the value is 14 Newton. Okay, 14 Newton. Okay, so very easy. So let's go to the part B. Okay, so it asks, what is the magnitude of the gravitational force between those same two protons? Okay, so for the gravitational force, we will use this formula, which have a similar form. Okay, for the gravitational force, so this is the gravitational coefficient. Okay, so this is actually 6.67 times 10 to negative 11 times, for the mass of the proton, it is 1.67 times 10 to minus 27 kilogram, and then square over the same distance square, 4 times 10 to minus 15 square. So this value is actually 1.2 times 10 to negative 33 Newton. Okay, so this is the number. So the story begins like this. Okay, so actually in the universe, we have 4 fundamental force. Okay, 4 types of force. Okay, we have electromagnetic force, 电磁力 EM force, 电磁力 we have gravitational force, 重力 OK, 还有2种什么 strong force and then weak force. OK, 也许你学那个中学物理的时候有提过吧？我不确定。反正就是这个宇宙里面有4种基本力了，有电磁力，那这个学期会学很多电磁力。那有 gravitational force 就是那个万有引力嘛，就是这个嘛。那这2个的话，就一般基础的物理不会学到了，就是。Strong force 的话就是跟这个东西有关了 ，weak force 的话就是跟一些核反应有关，就是一些什么那种什么核裂变啊、核聚变那种nuclear fission 有关，就是那种就是弱力嘛，就是你平常就是你小学的话就会。看过一个式子叫做 E equals mc square， 就是那个质能转换方程嘛，就是能量跟质量可以换，但是它换的条件很受限制啦。那就是那个核反应的条件嘛，就是一些比铁重的一些元素啊，它就是可以透过减少它的质量变成能量嘛，就是那种什么原子弹那种形式嘛，或者核聚变的话就是比铁轻的，就是那种什么氢弹啊，或者是对啊，就那种就是原子序比较小的那个粒子，它就可以也是透过减少质量，然后换取能量。那这个是 weak force 啊，那反正这些就是大家没学过嘛。那一般中学物理或者是大学物理的话，主要是学前面2个嘛。那现在就列举了。Okay, so for the question A, it asks you just calculate. Yeah, this is the electromagnetic force. It's 14 Newton. This 14 OK， 它太爆炸了，所以就删一下。就是这个是电磁力啦，电磁力就是告诉你说它会排斥，因为两个都是质子嘛，两个都是正电荷 ，both of them are positive charge, so they will repel each other. Okay, so this is gravitational force. This is gravitational force. So which means that this force is telling you how these two protons are attracting each other due to their mass. But this force is much smaller. Okay, 10 to negative 35. 10 to negative 35. This is 14. This is 14. This is 14. So this is much larger than the later one. So you may need to think of why the proton. Okay, in the high school chemistry, the teacher tells you that all the proton and neutron will just stay in the nucleus. Yeah, but actually there will be strong electromagnetic force that repel the proton. Yeah, but the gravitational force to attracting them is so weak, much weaker than the gravitational force. Why the nucleus can be stable there? Okay, so actually, for some even advanced physics, okay, they will have something called the standard model of the elementary particle. 这个叫做粒子的标准模型。Okay, so here we can see we have something called the quarks, 夸克，还有一些叫做氢子，就是一些很轻的粒子嘛，就是 leptons. And then we also have something like the boson, okay, boson, 玻色子 okay. So actually for a proton, if I remember correctly, it is actually built up by 2 up and 1 down. And for the neutron, okay, so it is actually building up by 1 up quark and 2 down quark. Okay, so you can, if you have interest, you can slightly go in it. You can see it shows the mass is something like something mega eV per c square. Okay, what is that? Usually you consider the SI unit for the mass is kilogram, but here is MeV over c square. So this is actually something like the E equals mc square. Okay, so this is the mass. This is the energy. Okay, so MeV is a unit for the energy. Okay, so this c square is actually the speed of light. Speed of light, 光速. Okay, so actually this is like the energy divided by the c square. Okay, will be the mass. Okay, will be the mass. And then here you can also check that the charge here is 2 over 3. 2 over 3. And then this is negative 1 over 3. So if you just have 2 times this number plus this number will be positive 1, which will be a charge of a proton. And then if we have 1 times this one plus 2 times this one, which will be 0, which will be the charge of a neutron. Okay, so you can, if you have interest, you can try to check it out. And also you can see electron is also elementary particles, 基本粒子. So you cannot further separate an electron into smaller particles. OK, 所以这边的那个基本粒子的意思是，这个高中你们学的那个是原子、中子嘛？那实际上透过一些方式你可以把一个原子跟一个中子再打得更散，变成一个夸克。那夸克能不能再更打散呢？目前是不可以，未来可不可以我也不知道。反正就是目前的话，最小的所谓的基本粒子的话，就是在这个表上面，但有很多东西还没发现。 那这个表发现的所有那个粒子啊，占我们这个宇宙里面多少？5%，5%在这个表里面能够解释的，解释不了的，有所谓的 dark matter， 暗物质。那引入了暗物质之后，它占我们宇宙的多少？25%啊，两个加起来25%左右。那剩下的是什么？叫做 dark energy 啊，暗能量。OK， 这些是比较玄学的东西。那有兴趣的话，自己可以 Google 一下了。那反正的话就是稍微提一下，就是有这个粒子模型。那提这个来干嘛呢？其实这里边有一个叫做 gluon 的东西啊 ，gluon。那你英文好的话，你知道一个字叫做 glue， 就是那个胶水嘛，就是它的中文叫做胶质嘛。即係好膠㗎嘛，咁啊可以 ，so it can be used to glue the proton and neutron together, so that yeah you can see for the gluon, it don't have any mass, okay, so actually the gluon is like 就是像那个胶水那样把那些夸克粘在一起。然后让它可以维持着一个原子核的状态 ，OK， 所以就是物理学家就是为了去解释这个世界的现象嘛，就是他们在想这个有什么问题，那个有什么问题，就比如说就想这个电磁力那边那个重力抵消不了嘛，那有什么方法可以让它解释得通呢？他就引入一些其他的例子。OK， 所以这个 sample problem 21.4 就是为了说这个故事，它的计算都非常简单。Okay, so let's finish this chapter quickly. So and then we have a 10 minutes break. Okay, so here is talk about charges conserved. 电荷守恒。Okay. So it means that the net electrical charge of any isolated system is always conserved. Okay, so here it says if we have two charged particles undergo an annihilation process, 就是那个湮灭的过程这个是叫做湮灭。They have equal and opposite sign, 所以有所谓的负电子。平常我们的电子跟一些正的电子，它们碰在一起，就是那个反粒子anti particle， 那它们就互为那个 anti particle， 那反粒子碰在一起的话，它们就会消失，变成能量。Okay, so it becomes something like the gamma. Gamma is something like the high energy wave, high energy particle, something like that. Okay, so if two charged particles appear as a result. Yeah, so also we may also have something like the energy and then separate into electron and positron, positron 变成电子跟正电子。OK， 那在我们的地球上有这样的东西存在吗？那是有的，就是打雷的时候就会有这些粒子的产生的。Okay, so here we simply talk about the electromagnetic spectrum because here we slightly talk about the gamma wave. Okay, so here you can see gamma ray. Okay, so gamma ray is actually a type of the electromagnetic wave, EM wave, 电磁波. Okay, so actually for the EM wave we have a large spectrum. 有一个很大的一个电磁波的光谱 ，OK， so from very low frequency up to very high frequency. From very low frequency, it will be something like the standard RF so-called the radio frequency. Yeah, so you can see here is the AM radio or FM radio. FM radio is like 100 megahertz, 100 megahertz here. And then, yeah, for the AM radio is even lower frequency. And also we can simply see that we have several axes. Here we have the wavelength. Wavelength is 波长. Okay, and then this is a frequency, 频率啦. Okay, so what is the relationship between the wavelength and the frequency is actually C equals F lambda. Okay, 波长 is lambda. Okay, this is FO. Yeah. So C equals F lambda, and then C is the speed of light again. Speed of light. Okay, which means that if the frequency is higher and the lambda is shorter, okay, so you can see this axis is like 10 to the 6, 10 to the 7, all the way up to 10 to the 20th. And in this axis, 10 to the 3, 10 to the 2, 1, and then 10 to the -1, all the way up to 10 to the -12. Okay. So here, also we should notice that there is an other formula, like E equals HF, or sometimes we will write it as H nu for the frequency, but anyway, it's just a frequency. So which means that this is actually the energy of a photon. Okay, which means that if a photon have a higher frequency, then the energy inside a photon will be larger. Okay, so here you can see that this is 10 to the -9, this is 10 to the 6. Okay, so on the right side, we will consider they are high energy particle. Okay, so you can see here on the right side we have gamma ray, we have X-ray, soft X-ray, hard X-ray, we have ultraviolet, we have visible light, just narrow like this, and then we have infrared, 红外线、可见光跟紫外线在中间. Okay, and then on the left side we have microwave. Yeah, also you can see, actually for this range is so-called the radio frequency, or even lower radio frequency. So let's say if we have a 2.4 gigahertz, 5 gigahertz is for the Wi-Fi, and then all the 3G, 4G, also some of the frequency here, starting from hundreds of megahertz to several gigahertz. And for the 5G communication, we may use up to something like 29 gigahertz, around 29 gigahertz for the 5G communication. So you should distinguish this 5G, the G, and this gigahertz, the G in the gigahertz are different. This is for the gigahertz. This G means 10 to the 9th power. But for the communication sense, 3G, 5G, 4G, 5G, the G means the generation. 第几代了? Generation. Okay, so they are different. They are different things. Okay, so anyway, for the electromagnetic spectrum, starting from low frequency, we have something like the AM/FM radio. We have something like the for the wireless communication, the Wi-Fi, and then the wide range communication, and then for the even high frequency, we will have the infrared, visible light, ultraviolet, and then for the even higher frequency, we have the X-ray, and also the gamma ray. Okay, and this is so-called the high energy particle. Okay, so so here we have additional example. Maybe we can just skip it. So let us do this one. yeah, to finish this chapter. Okay, so for this additional example, it says 3 identical conducting spheres initially have following charges: sphere A 4Q, sphere B negative 6Q, sphere C 0. And then sphere A and B are fixed in place. Okay, so they can move with a center-to-center separation that is much larger than the spheres. 2 experiments are conducted. Okay, in experiment 1, sphere C touch A first, and then separately to touch B. Okay, and then it is removed. And then experiment 2 is starting with the same initial state. The procedure is reversed. Sphere C touch B first, and then separately to sphere A, and then it is removed again. Okay, so this is the they have a different order. First A and then B for the experiment 1, and then for the experiment 2 is first B and then A. Okay, so it asks you what is the ratio of the electrostatic force between A and B at the end of experiment 2 to that at the end of experiment 1. Okay, so as much as the touching order is different, so the final state will also be different. Okay, so it means that suppose for the experiment 1, suppose we have A, B, and C. Initially, A have a 4Q, and then B have a negative 6Q, and then C have 0. Okay, for experiment 1, for the first step, we touch A and C. Okay, which means that B doesn't change, so it still have 6Q. And for when we touch A and C, the charge will be equally separate to sphere A and C. So here we have a 4Q plus 0 will be 4Q, and then divided by 2 will be 2Q. So we have 2Q and 2Q here. And then for the next step, we touch sphere C with sphere B. Okay, so B and C. Okay, B and C. So A doesn't change. And then here we have a negative 6Q plus 2Q will be negative 4Q, and then divided by 2 will be negative 2Q, negative 2Q. Yeah. Okay, so and then for experiment 2, at the beginning we also have 4Q, negative 6Q, and 0. But the first step will be touching B and C, so A doesn't change. And then for B and C, negative 6Q plus 0 will be negative 6Q, divided by 2 will be negative 3Q, negative 3Q. And then for the next step, touching A and C, so B doesn't change. And then here we have a 4Q minus 3Q will be Q, and then divided by 2 will be Q over 2, Q over 2. Okay, so in such a way, we would like to calculate F2 over F1 will be K times Q over 2 times 3Q, Q over 2 times 3Q. Okay, so the force between A and B, which means that we consider these two values, and then of course taking the absolute value, so that we just ignore the minus sign, and then over D square. Okay, actually we don't really need to care about what D is, because D will eventually cancel. And then we also consider these two values, so we have a K times 2Q here, and then over D square. So finally we can actually cancel this D square, K, Q. Okay, so finally the answer will be 3 over 2 over 4, so which will be 3 over 8, which is 0.375. 0.375. Okay, so yeah, so and that's the end of this chapter.